Hi, I'm Dr. J, and this is a guide about discrete random variables. It's the second video in a two-part or multi-part video series, so you might want to go back to the previous one. There's a link in the description for that. There's also a link in the description for the slides in case you want to print them out. So the last video we talked about distinguishing discrete versus continuous random variables. This video is all about discrete random variables. Okay, so discrete random variables are those random variables that have a finite or countably infinite range or set of possible values. Alright, so we're going to start out talking about the distribution. The distribution of a random variable x is just the collection of all the probabilities associated with that random variable. For discrete random variables, we have something called a probability mass function that can define a distribution. That probability mass function, or PMF, basically just says, hey, for this value of this random variable, this is the probability. So it's just a function that takes in the possible values of the random variable and tells you the probability for that random variable. So the easiest way to think of it, or to see it in notation, is this capital P for probability. Capital X, the random variable, is equal to little x, a possible realization. For example, like probability x is equal to 1, for instance. Going forward, it's actually going to be more convenient to use the other notation, this subscript, or this little p with a subscript x as a function of that realized value, little x. Say p subscript x of 1, for instance. We also have something called the cumulative distribution function. So the cumulative distribution function, the cumulative in the name, basically means it's going to take all the probabilities from as far down as you want to go, all the way up to whatever value you're interested in. So this capital F, which is the standard way that we write the cumulative distribution function, or the CDF. Capital F is a function of any number, say capital F subscript x of the number 1. That would tell you what the probability is for the random variable x being less than or equal to 1. For discrete random variables, the way that we calculate this is basically just to calculate all the possible values in the probability mass function up until that number that we're interested in. So if we're interested in what the CDF is at 1, we just calculate the probability mass function for all the values in the range of that random variable that are less than or equal to 1. Thus, this notation here, we just take the summation over all the values less than or equal to little x. Okay, there's also some more notation here, or terminology really. There's the set of all non-zero probability values of x. That's called the support, right? Because it's the values that the probability mass function, which I should have written not as little f there, but as p subscript x of x, that function can take on. Everywhere else it's 0. And this is actually exactly the same as the idea of the range of x, the random variable. So a support and range, usually I'll probably use the term support going forward. Okay. All right, so we've got the probability mass function, the cumulative distribution function, and the support. So here's a few examples. And basically what I'm trying to get at within these examples is to describe when something is a valid probability mass function and when it's not. And basically what has to happen is that you have to obey Kolmogorov's axioms of probability. Alright, so what you should do on this slide basically is to stop. So I'll introduce, here's an example. The random variable can possibly be -3, -1, 0, 5, 2, 7, rather, with probabilities 0.1, 0.45, 0.15, 0.25, and 0.05. So you should pause right now and you should think to yourself, all right, is that valid? That is, are all the probabilities non-negative? Do all the probabilities, the collection of probabilities, sum to 1? The third Kolmogorov axiom is kind of taken as it must be true with tables like this. Alright, so with this particular example, yes, it's in fact true because those probabilities are all positive and they sum to 1. Note here that the values in the support of the random variable don't have to be positive. So -3 and -1 are totally reasonable. It's the probabilities themselves that have to be non-negative. Alright, here's the second example. Right, so you should pause the video right here and think to yourself, alright, is this a valid PMF? Okay. It's not a valid PMF, and it's not a valid PMF because the probability of being equal to 3 is negative, and we cannot have negative probabilities. Alright, here's a third one. Again, stop the video. Okay, and then look at this and say, do I think this is a valid PMF or not? And if you look closely, and if you add up those probabilities, you'll find out that no, in fact, it's not valid because those probabilities sum to 0.99, which is not 1, right? Okay. All right, so just some examples of probability mass functions for discrete random variables. All right, so here's another example. We have back to our rolling of a six-sided die. When we roll that six-sided die, we might say that y, a random variable, is the number of pips or number of dots here on the upturned face when we roll it. And we can describe a PMF and a PDF for that. The support of this random variable is just the values 1, 2, 3, 4, 5, and 6. If we believe that the die has equal probability, then that support with the PMF and the CDF are just, the PMF is just 1/6 on each of the sides because they're equally likely. And then we have the CDF, we just have to do a cumulative addition. And so the probability of being less than or equal to 1 is just 1/6. The probability of being less than or equal to 2 is the probability of being 2 plus the probability of being 1, so a total of 2/6. And we get 3, 6, 4, 6, 5, 6, and 6, 6, which is 1. Okay, that's rolling a six-sided die. Dragonwood, which way should I go here? Dragonwood is a game that I gotta go this way. Dragonwood is a game that I like, especially for illustrating probability and expected value that we'll talk about in a second. It's got six-sided dice, but these six-sided dice are unique because they have only 4 numbers. So it goes 1, 2, 2, 3, 3, and then 4. Let's see if I get all the sides there. Okay? And the way that this Dragonwood game works is that, before we get there, let's just talk about rolling these dice. So in the game, you're basically going to roll these dice, however many you get for that particular turn, and then you're going to add them up. All right? And so right now, you might want to stop the video and see if you can figure out what the support, PMF, and CDF are for rolling, 3, I don't have a third one, rolling 3 Dragonwood dice. Okay, so stop. All right, now support is relatively easy because you can just think about what's the minimum, what's the maximum, what combinations can I get in between. So the only way to get the minimum you can get is rolling all 1s on 3 of your dice, so the minimum is 3. The maximum is rolling all 4s on all of your dice, and there's 3 dice, so that's a total of 12. And you can get every combination in between. So the integers 3 up to 12 are the possibilities for the support. Now, the PMF and CDF are a little bit more difficult to figure out. And in fact, I kind of made it easy on myself. And instead of sitting down and doing all the calculations, I decided instead to let the computer do it. Right? Good trick. Let the computer do it. And what I did in the computer is I just programmed up an imaginary set of dice, and I'm rolling them, and I'm adding them up, and I'm doing every possible roll and every possible combination of sides on this dice, which means that when I'm looking at this dice, there's 2 ways to get a 2. There's this side here, right? And there's this side all the way on the other side as well. And so when I do that and I write the program, here's what I get. So we have, again, the support is 3 up to 12. And then the PMF, right, which I calculated via this code in the statistical software R, says, all right, the only way, the probability of getting 3 is approximately 0.005. If you do the calculation yourself, you'll see that it's, I think, 0.0046, so this is rounded a bit. And then, we can do all those PMF calculations, and then the CDF, the cumulative distribution function, is just the cumulative addition, or the cumulative sum of those PMF values. So for x equals 3, we have the same value, but then for x equals 4, we have the sum of the PMF for x equals 3 and the PMF for x equals 4. All right, so that's a little bit an example of using this idea of discrete random variables, the PMF and CDF and support in the context of Dragonwood, this game. Here's a visual representation of that probability mass function and cumulative distribution function. Again, the left figure shows you the probability of observing those particular values. So there's a relatively small but non-zero probability value of seeing a 3. Larger for 4, 5, 6, 7, and then 7 and 8 are equally likely. And then it starts going down to 9, 10, 11, and 12. Any value outside those gets a probability of 0 because they're not possible when rolling 3 of these Dragonwood dice. On the right side, we see the cumulative distribution function. Now, this cumulative distribution function here shows you that If you're looking at the probability of being a 2, for instance, right? Sorry, 2 is a bad example. Probability of, let's say 6. If you go to a probability of 6, you just go to 6 on the x-axis and you go up. And that is just a little bit over 25%, maybe 26%. But you'll notice that if you go to the right a little bit, so if you go to what's the probability of being less than or equal to 6.6, right, it's the same. And it's the same because you can't get a 0.6 when you're rolling these dice. And so the next hop or jump in this function happens at 7. So at 7, the probability of being less than or equal to 7, it turns out to be 0.5. Okay, so here's, for those who like functions and like thinking about functions, here's just some properties that might be of interest to you. So a probability mass function, or P sub x of x, is a value, probability is a value between 0 and 1, which possibly could include 0 and 1, and that's true for all real numbers, not just the numbers in the support of the random variable. If you do add up all those random variables in the support, then those sum to 1. For the cumulative distribution function, you get some similar properties. First off, it's always between 0 and 1, and it's non-decreasing, that is f of x, well, it says it right there, right? It always goes up, right? Or at least it never goes down. That's what I should really say. The limit, if you take it all the way to the left, is 0, and the limit to the right is 1. And it's right continuous, and you actually saw that in the other picture before. Okay, so that's just some interesting properties in case you're interested in that kind of thing. Alright, if we go back to thinking about Dragonwood. Dragonwood, the game, is really played by having a set of cards in your hand. These are the cards. And based on what cards you have in your hand, you get to roll a certain number of dice, or which cards you want to play. You get to roll a certain number of dice. And your goal then is to capture monsters. So here are the monster cards. Let's see, there we go. Right, so here's an example of some monsters. And so basically, if you look here real closely, this is the victory points right there that you get for the monster. And then depending on what kind of cards you play, you'll get, or how many cards you play really, you get to choose one of these 3 here. So I'm going to use always the, I think it's the strike. So in this example on the slide, suppose that you have the option of hitting these 3 monsters. You have the possibility of hitting the spooky spiders for 1 victory point, or the possibility of hitting the hungry bear for 3 victory points, or the chance of getting the grumpy troll for 4 victory points. There we go. But the issue is that there's increasing defense on these creatures. So the spooky spiders have 3, the hungry bear has 7, and the grumpy troll has 9. And for whatever reason, with cards you played, you have 3 dice to roll. So the question is, which of these should you choose? And obviously there's more going on to the game, so let's just ignore that and say, if these are your only 3 options, which are you going to choose? Now some might say, well, I'm going to choose the 1 victory point because I know that I'll get it. Because with 3 dice, there's no way that I get anything less than a 3. Okay? But somebody else might say, but look, if I go after the 4 victory points, then if I get it, then I get more. Right? So, what do we do? Alright, so one thing you could do is you could calculate, well, what's the probability that I'll be able to get this particular monster? And so, in order to calculate the probability here, because the game says we have to roll dice that are equal to or greater than the defense, is to use the CDF that we had a couple of slides ago, and say, well, the probability being less, let's say, the probability being greater than or equal to 6, that's equal to 1 minus the probability of being less than or equal to 5, right? So that's this defense minus 1. So for instance, if x is this random variable that's the sum of our 3 Dragonwood dice, and we're looking for the probability that x is greater than or equal to 3, okay, well that one's simple. That's just probably 1 minus probably that it's less than or equal to 2, but we have to have 3, so we know that that's 1. But the other 2 are maybe more interesting. Maybe I should have put some pauses here. If you have, what's the probability of being greater than or equal to 7? That's equal to the probability of being less than or equal to 6. And if you go back and calculate this out, you'll find that that's 0.722. Probability of being greater than or equal to 9 is 0.278. And that's fine, but we almost already knew this. Right? We knew that it was going to be easier to get the 1 victory point than to get the 3, which would be easier than getting the 4. So this really hasn't helped us too much, other than to know, okay, well maybe the 4 is kind of hard to get, right? So what we might want to do is we might want to say, let's multiply that probability times how many victory points we would get if we got it. And we're going to call that perhaps the expected points. Okay, so if we do that, we find that, all right, take 1 times the probability of being greater than or equal to 3. That's 1 because we always are. 3 times the probability of being greater than or equal to 7. That's 2.17. And we take 4 times the probability of being greater than or equal to 9. And that's 1.18. So one approach to making this decision is to say, I'm going to choose the one that has the highest expected points. Right? In this case, it was going after the 3 victory point monster that had a defense of 7. Right? Because you're expected to get 2.17 victory points when you do that. Okay, so that brings us into this idea of an expectation of a random variable. All right? The expectation of some function h of the random variable is this right here for a discrete random variable. It's just the sum of x calculated at each of the possible values in the support for the random variable x times the probability that x takes on that particular value. So the intuition here is that this is just a weighted average of the possible values where the weight is the probability. All right? The most common expectation that we're interested in is when h is just the identity function, so the simplest thing we can imagine. And this right here is called the expectation of the random variable x. And oftentimes we want to make this succinct, and we might use the Greek letter mu to indicate the expectation. Alright, so if we go back to the Dragonwood example, what is the expected value, say, of rolling 3 dice, even though I only have 2 here? You could probably figure it out in your head, but if there's 1, 2, 2, 3, 3, 4, and each one has a 1/6 probability, you can do that and you find that the expected value of a single die is 2.5, and then so intuitively expected value of all of them must be 7.5. Here I've actually used R to do the calculation based on the probability mass function that we derived before, multiplying each of those values times the value of the random variable and adding them up, and in fact you get 7.5. I want to comment here perhaps a physics related interpretation for this expected value. So you can think about this expected value as being the center of mass. So you think of a ruler or something, and now what you're going to put on that ruler are weights. Those weights are going to be proportional to the probability, and they're going to be located at the values of that random variable. So for instance, at the value 3, let's just show the picture, at a value 3 we're going to place a weight that's proportional to 0.005. Then if we go up to say 7, we're going to put a weight there that's 0.23 or so. And if we have this ruler, that's really the x-axis in this picture, and we have the weights that are associated with the probabilities, the center of mass is the place where this thing exactly balances, which in the picture is the red triangle there at 7.5. Alright, so that's the expected value of these 3 Dragonwood dice. Here's another example. This is an example we'll probably use going forward. It's the idea of flipping a coin. So we've got a coin here, but instead of a standard coin that might have a 0.5 probability of being flipped heads and a 0.5 probability of flipping tails, we have a biased coin somehow. Somehow it's weighted, or the way that we're flipping is biased. And it turns out that the probability of being heads is P, and the probability of being tails is 1 minus P, where that P is, say, not 0.5. And the way that we've coded this up is we've said, let's let 1 be a heads and 0 be a tails. Alright, so you should stop right now, use the definition for expected value, and calculate the expected value. Stop. It turns out the expected value is P. If P happens to be 0.9, then this is a picture of that particular situation. So we have a big mass at 9, we have 1/9 of that at 0. What did I say? We have a big mass at 1, and 1/9 of that at 0, and that's going to balance exactly at 0.9. That's going to be the center of mass, or this expectation. Alright, so here's some properties of expectations. This is a good one to remember. If we have x and y are 2 different random variables, and we have some constants a, b, and c, those are just some numbers, then it turns out that the expectation of a times x plus b times y plus c is just equal to a times the expectation of x plus b times the expectation of y plus c. And we actually used this a little bit ago when we did the dice example, right? So for an individual die, the probability is 2.5. If we have 3 of them, we added them together, we got 7.5, and we were actually using this property right here. So this is the overall formula that's good to remember, but some special cases are also good just to have in hand. The expectation of x plus y is just the expectation of x plus the expectation of y. The expectation of a constant times a random variable is just the constant times the expectation of the random variable. And the expectation of a constant is just the constant, right? What do you expect something that's random but not really to be? You just expect it to be itself. Alright, there are a couple of other cards in the game of Dragonwood. So these two cards right here, we have the Friendly Bunny right here, and we have the Cloak of Darkness right there. And they allow you to help out your rolls. And so the Cloak of Darkness in particular just always adds 2 to any time you're trying to get a monster. And the Friendly Bunny allows you to roll an extra die, but only once. So once you use this card, then it's gone for the rest of the game. So the question on this slide is, alright, well, what's the expected attack roll? If you're rolling 3 dice, you have the Cloak of Darkness, and you opt to use the Friendly Bunny. Well, using that properties of expectations on the previous page, we already know what the expected value of the 3 dice are. That was 7.5. And we talked about one more die coming from the Friendly Bunny. That's expected value is 2.5. And the Cloak of Darkness always gets us 2, so that's a constant. And so what we have is this setup. So x is the 3 dice, y is the 1 die. The expectation of x plus y plus the constant, alright, is just that. Expectation of x plus the expectation of y plus that constant for a total of 12. That's the expected die roll in that scenario in the game. Okay, so we talked about the expectation being one example of the expectation of a random variable, right, using that function. Here's another one. It's called the variance. So the variance is defined as the expected squared distance from the mean or from the expected value. So right here, that's where we're using mu to be the expected value of x, right? No function at all, or the identity function, if you will. So the variance is the expectation of this quantity, random variable, minus its mean squared, right? And because it's an expected value, you can calculate it as a weighted average, where the weight is the probability across all possible values for that random variable, xi, and add them up. And if you do it, that's called the variance. Usually, if we want to make this succinct, we use sigma squared to represent the variance. And I just want to make a comment here, I won't go into detail, but this is analogous to the moment of inertia in physics, just like the center of mass was analogous to the expectation. Sometimes we talk about the variance, but more commonly, and we'll talk about why in a bit, we will use the standard deviation, which is just the positive square root of the variance. And if we want to use this particular value, we will call it sigma. Okay. Alright, so that's the variance. Here's some properties of variances. And now this piece is important. The random variables x and y have to be independent in order for these properties to be true. We haven't talked about independence of random variables yet, but it's related to independence of events. The key here is that for 2 random variables to be independent, then their joint probability mass function, that's indicated here by the p subscript x comma y of x and y, that's just the probability that x is equal to little x and y is equal to little y, that joint probability is equal to the product of the marginal probabilities for x and for y, represented here by p subscript x of x and p subscript y of y. Okay, so I'm not going to go into too much detail here, partly because we will be using an assumption of independence quite a lot, as opposed to lack of independent random variables. Of course, when we get to regression, that's not kind of true. Okay, so if you have independence, then this is a relationship you have between 2 discrete random variables. And so if they're independent and you have these constants a, b, and c, and you want to take the variance of this function, or this sum, a times x plus b times y plus c, then it turns out that you have to take a squared times the variance of x plus b squared times the variance of y, and c gets dropped out. So again, this is the general formula. For the formula that is a little more specific, we have the variance of a constant is 0, right? If it's a constant, it doesn't vary, so the variance is 0. If you have the variance of a constant times a random variable, when you pull that constant out, you have to square it. If you have the variance of the sum of 2 random variables, then it's the sum of the variances if the 2 are independent. Okay, so if we go back to the Dragonwood example, we can calculate the variance of the sum of 3 Dragonwood dice. And again, we're going to do this computationally using R. So if we do that, we find out that the variance is 2.766. We take the square root of that, and we get the variance, which is 1.66 or so. Alright, so as a last slide in this video, if we have that biased coin, so we've got our good old friend here, the coin, but it's biased, so it lands with heads with probably P and tails with probably 1 minus P. You should stop right now and see if you can figure out what the variance is of that coin. It's going to be a function of P, so I'll stop. Alright, and if you do, you'll find that the expected value, which we just drove before, is P, and that the variance is P times 1 minus P. So then the next question for you, what value for P maximizes this variance? So again, you should stop, right, and try to figure that out. Okay, it turns out that if you draw a picture, this is sort of easy. If you know derivatives, it's pretty easy. It turns out that it's going to be maximized at a value 0.5. Okay. Alright, so that was part 2 of this video set on discrete random variables. The next one is going to be talking about specific discrete random variables. We're going to talk about, probably in 3 different videos, Bernoulli, binomial, and Poisson. Catch you there.